Eric R. Johnston. You have his bio on the website. The book that he wrote is on the table. You can see it. And as I said, the first person who asks a question at the end gets a free copy of his book. I wanted to point out one thing, and then I'll let him introduce. This is the announcement on one of his co-authors' blogs of the book. The book came out in O'Reilly last August. And the entire argument behind why this book is indeed extremely useful is that the intention of the authors was very clear. Provide a programmer's guide to quantum computing, but removing in the process all the mysticism that people currently experience before they can start tinkering without needing a PhD in quantum physics to actually write meaningful working programs. The question is, should semiconductor physics be a prerequisite before you go and write your first Python program? And the answer is obviously no. So what the book is doing, and EJ is going to present this very clearly, is they came up with, so you've seen examples in Qiskit, but they came up with their own language, which is based in JavaScript and runs in the browser. And I'll let EJ take it from here. So how about we welcome him for his book.
Thank you. How's the audio level okay?
Yeah.
Okay. Well, thank you guys. Thank you all very much for coming. I'm very excited about this. As Adrian mentioned, I'm Eric Johnston. I usually go by EJ. And with a couple of colleagues, I wrote this middle book, which is the O'Reilly Programmer's Guide to Quantum Computers. And really also, it was a hugely collaborative effort, including people from various companies, and including James Weaver, who's one of the other speakers today, who helped a lot when we were trying to get the thing hands-on, kind of trying to make sure it's what O'Reilly is known for, which is that practical hands-on programmer's guide. It's really for quantum curious coders, not for physicists. So let's see, here. All right, just very quickly on my own background, because you'll see why it's relevant. I have a bachelor's in EECS from Berkeley. I'm not a physicist or strictly a mathematician. I started the quantum computing research on my own as a kind of an obsessive hobby. I was also on their gymnastics team. And then I worked right at the end of college and out of just afterward at NASA Ames Research Center. And we're just when kind of large real-time graphics supercomputers were starting to become accessible. And you'll see a little bit of that and it'll become relevant, I swear. I also spent a long time working for most of my career, including while I was an undergrad, paying for college, writing video games and computer games for LucasArts, and then also doing special effects for movies at ILM. And then much more recently, I did postdoc research, and postdoc has an asterisk because I don't have a PhD, but that was the research position they had open. So they said, not my problem. And my role at that at University of Bristol Center for Quantum Photonics was to be an engineer immersed in the projects going on by the physicists there, because nobody there is doing kind of idle research. They're all building devices, and so the only way to help them get things built was to try and understand their research. And I loved that. And at the end of it, which I didn't know was going to be the end of my time in Bristol, one of the projects, which is a universal fault-tolerant quantum computer using photons as qubits, spun off as a startup company, which is now called SIGCSE, and I'm their first engineer. And so, let's see. what we'll see also is the book is focused on using fault-tolerant quantum computers. It shows you how to use existing quantum computers as well, but it's really kind of geared toward machines that are coming in the future. So first, a few things that you don't know about the book, and really kind of nobody but the authors knows about the book. It was not supposed to be the octopus book. It was supposed to be the tardigrade book. And that's mostly because, so I don't know if you're familiar with tardigrades, but they are small and weird, and they can survive for quite a while at temperatures down to 1 Kelvin. So they actually could live inside a quantum computer, which we thought was pretty cool. And they're also adorable. And then the next thing is that this is a book that I started writing in 1999. And this was exploration on my part, and I got it wrong a lot of the time. In fact, this adder, which is actually one of the examples in the book now, this is a terrible implementation of a 4-bit adder. It works, but you wouldn't do it this way. It took meeting my co-authors at Bristol to fill in a lot of the gaps and stuff that I as an engineer was missing. And in a sense, I feel like I am the target audiences that we were talking about in the prior session, in that the exploration is super important, and a lot of the physics background I was just straight out missing. So I got a lot of stuff wrong. And let's see. So the third thing that's I think key to this whole to the existence of the book and the learning process that we are attempting to put forth in it is this notation. So this is what we call in the book circle notation, and really all it is each circle is one term in your quantum state, and it's a complex number. It has a magnitude and a phase. However, the reason that I started using circle notation in 2002 was that I couldn't understand I could understand what ket notation was, but I just couldn't look at a whole page of it and make sense of things very well as somebody with a strong programming background. And so I started to sketch out things where each complex number, each value was just one of these kind of directed circles. And then what I discovered, well, first we have, it's required to have a Feynman quote if you're talking about quantum computing, and this is my favorite, which is that new notations really can lead to breakthroughs. And in my case, it was a personal breakthrough. I knew nothing about quantum computing, and now it's my career. But also, here is what we're looking at here is an actual screenshot from when I was working on a computer graphics thing that became one of the book chapters. And in this case, I had just given up trying to do a noise redistribution using a quantum computer for kind of image sampling. And I had just given up and decided to go to bed, and rubbed my eyes and leaned back. And when I opened my eyes again, they were a little blurry. And what I noticed is the vertical waves going down here. So in this is 10 qubits. So it's 32 by 32 terms, which is 1024 terms for your quantum computer. And if we read all 10 qubits, all of these circles are going to become empty except one. We'll have one value that wins. And the darkness of each circle in this case is going to be the squared length of that vector. And so that's the same as the probability that that circle will be picked if we were to read all of this stuff. And so what you can see just intuitively and very, very visually is the waves going from top to bottom. And In this case, I was doing a quantum Fourier transform, trying to pull this information out. And what this caused was a realization that the Fourier transform was the right thing. And it turned out I was doing it backwards. And so just kind of poking at it a little more, the algorithm was actually successful and produced a substantial gain in kind of an interesting noise redistribution program. So this really is what circle notation is for. It's so that you can glance at a quantum state and try and figure out, well, yeah, it kind of get an intuitive sense for what needs to happen. It's making it into a sliding puzzle, really. And we'll see a bunch of that in a moment. So the next thing about this is that on the sample page, so the book links to programming samples, and on the sample page, in addition to kind of all of the things that you normally have to learn while you're learning quantum computing, this is implemented in JavaScript just so that we can run things online, right, and have them be interactive and not have anyone need to install anything. It'll even run on a mobile phone. But the thing that we ended up doing before publishing the book, as we were talking to people like James Weaver and then also Maria at Microsoft, is we started porting these samples so that this is in JavaScript, which isn't everybody's favorite language to do anything serious in, other than web development. There's Qiskit, which will be shown a bunch here later, this is the exact same sample ported to that. And then in order to run it, there are instructions. As soon as you click run, it shows you that, it kind of gives you the place that you go to run it. OpenChasm for running things on a physical one of IBM's machines. Q#, which we're going to see later on today. And so see the OpenChasm version is, in all cases, it's right here. And not only that, the programs are just in GitHub, so people can get them. Many of the translations, including the Q# translations, were submitted via pull request to us, to the authors. So it's become kind of a Rosetta Stone watering hole for learning quantum computation and actually seeing the same program translated into several different languages. So that, I hope, is as valuable a resource as the book itself. But that gave me a terrible idea, which I then followed through with, which is if you're reading the book on a Kindle and you click on the link, which normally you would type into your browser or click on your iPad or whatever, it will actually run the quantum computation simulator physically on the Kindle, because the Kindle's little experimental browser is just powerful enough. It took a long time to get it to kind of get these so that the browser was okay with it, but it works. It doesn't run really quickly, but it's kind of fun to see it actually running, and you can edit the code and run it, and so you can write your own programs, and they'll run right in place. And then when you hit the back button, you go back to reading, which is pretty spiffy. And then some of you in the audience will recognize this. It's an HP 28S. This was actually my undergrad calculator, this physical one. And it is, in 1988, it was brand new. And then the battery door broke, which is why there's tape on it over here. And however, one of the big lessons here, as I started to tinker with it, is that for student projects, implementing a quantum computation simulator is really actually no big deal, and you don't need a supercomputer to do it. This machine has 32K of RAM total, right, including everything. Everything has to fit in there. But that is enough for 10 good qubits, because 2 to the 10th is 1024, and then you need 8 bytes per double precision float, so 16 for a complex number times 1024 is 16K. So you've got plenty of memory left over. You can't quite do 11 qubits because then there's no memory for anything else. And so that, however, is enough to run Shor really, really, really slowly, because I think I'm abusing the hardware in this case to do it. But there are little program buttons put in here, and implementing stuff like this is actually, I think, would be a great part of a curriculum, because it is, once you've implemented something as a computer science student, you get to keep that knowledge. Right? That's something that you can carry with you. So this is the actual Shor example that is in the book as well. The key problem with this is that there's no input. So as soon as I jostled the battery door, everything got cleared and I have to type it in again to run it. This is most of the source code. So we have our controlled knot, which we've been looking at this morning already, and Hadamard. These are the 2x2 unitary matrices, which kind of crammed into this little machine, and then a controlled unitary function. And for those not familiar, this is in reverse Polish notation, which is just a terrible way to write code, but it was a really fun project. All right. What I try to do when I'm speaking with classrooms, and also what I've tried to convey in the book, what all three of the authors have tried to convey in the book, is an intuition for quantum computation. Because if you can start to, as a software engineer, understand what it is, or as a computer science student, understand what it is, how the machine works and what it does, and not make it spooky, then I think you will get more people starting to play with it. That circle notation is key, and we'll see a little bit of that live in a moment. But also, I should mention, the book now has been used in at least 2 quantum computing classes. Carnegie Mellon and Rice University. I've been in contact with professors in both those places, and so even though that circle notation started as kind of a Wolfling thing, I guess it's starting to make headway. So intuitively, there's a lot of press and a lot of kind of popular writing about quantum computers being better than a regular computer. And it actually reminded me quite a bit of when the media was all over itself about Wi-Fi versus Bluetooth. And that was kind of missing the point. And eventually, we figured it out. But this conflict in itself is a very, very, very small part of what's going on. And as a programmer, not really that useful. What's more useful is to realize that a quantum computer, a QPU, so the quantum part of a quantum computer, is a coprocessor. And it has some parallels to a GPU. And I spent a huge amount of my early career on what we now call GPUs. And so it's interesting to take a look at the two side by side. And the book does this very, very briefly as well. But first of all, right, with GPUs, you have special instructions, and really it can be pretty tricky to program. It's something that not all computer science students really even get into, but the ones that do get passionate about it, right? So QPU, same thing, special instructions. With the GPU, it's very rare that anyone writes a program that runs entirely on the GPU. Mostly you write CPU programs, and then you use the GPU for library calls that fit to its strengths. So same with the QPU. So it's important for students to realize the CPU doesn't go away. All of the stuff that you have already, you still have, and just like a GPU or even a math coprocessor, you have it's an augmentation to a classical computer. And then also the GPU is on a separate clock and has special I/O. In that case, it's video output for monitors. The QPU it probably has several different special clocks, depending on what the implementation of the QPU is, but it may also in the future have things like optical I/O to be able to send quantum information. We also have GPUs can be tricky to debug. Sometimes the best approach is just to change your program and see what comes out. QPUs introduce something really interesting, which is fundamental randomness. A random number on a normal computer is usually pseudo-random. A random number on a quantum computer is actually core of the universe, really, really random. And so as applications get more complicated, we're going to see some really fun late night debugging sessions for sure. So the GPU has usually all sorts of weird memory that the CPU can't really access very well. The speeds for working with a GPU can be asymmetric, and in some cases, you can have faulty GPU memory in order to make it go faster, and that's just a mode you switch it into. With a QPU, as we've seen already in some of the earlier sessions, you have the entirety of the Hilbert space that your data kind of goes in and takes up while you're working with it, and when you read that, you're going to destroy it. So very similar to a GPU, you have all of this kind of memory that's not your CPU memory. Large GPUs, if you've ever seen some of the new graphics cards with 6 fans on them that look awesome, that is, well, large QPUs also need special cooling. And then the finished job of a GPU computation is usually an image. It's usually literally a projection of all of the data that the GPU contains. You don't see the 3D vectors and stuff like that. What you see is the projection onto a 2D image using the viewfrostum. With a QPU, when you read the quantum data, you are, again, literally getting a projection onto a particular subspace of the data that was contained there. Right. Optimizing for one GPU can slow down others. QPUs are so different from each other that that's currently very much the case. For example, if what you're trying to do is write code for a machine implemented via ion trap, if that's linear, then you may end up spending a lot of your time swapping qubits from one position to another. And so certain operations may be slower while others are fast. In fact, I think there was one machine we came in contact with at Bristol where a conditional phase between 2 qubits was very fast and very accurate, and pretty much everything else was slow. And then GPUs can be simulated. We used to do it all the time. They can't be simulated at full speed, or you wouldn't buy the real one. And obviously, that's the same with QPUs, where we commonly will write programs that won't complete in the expected life of the universe. And then this is a big one for me. In 1994, I gave a talk at SIGGRAPH, and it was showing real-time 3D GPU accelerated stuff for entertainment. And it was the question was whether it's practical for home use, right? And the GPU I was using was actually, at the time, it was the second one, the SGI Onyx. The first GPU I ever had contact with was not actually the one on the left here. It was a Skywriter, which is its predecessor. But this isn't that different from the form factor of a modern quantum computer. And so we did get a lot of questions as to how practical this stuff was that we were doing with GPUs. And then, of course, very quickly, we have GPUs in the home. The Nintendo 64, I was on the development team for the first Nintendo 64 game that Lucasfilm did, called Shadows of the Empire. And while we were developing that, we had 2 Onyxes because that was the only machine capable of simulating the Nintendo 64. And then obviously, the graphics capability of Nintendo 64 is outpaced by everybody's phone now. All right, and then the last thing I want to drill in before we get into some fun live demos is that in the 90s and the 80s, GPUs weren't really on people's radar. So with computer science students right now, quantum computing may be something that they take and learn about, but don't really spend time tinkering with, because it's just not kind of in the mainstream. So my second commercial software project was porting an Indiana Jones adventure game from the PC to the Mac at the time. And when you have teams developing games like this, which this was the state of the art for home entertainment at the time, this doesn't use floating point. It certainly doesn't use 3D graphics, and it's not clear why you would use 3D graphics. And so any discussion about a GPU on the development team of a game like this would be kind of a short one, because it's not really it's not really being pursued at all. And then, of course, a very small number of years later, 2008, we have not only GPUs, but every 2D game is actually running through a GPU as well, pretty much. And the thing about this that would have been completely unfathomable, besides the amount of floating point math being done per frame, is that every pixel in this image is running a pixel shader that is actually longer than the first game I ever wrote. So it's a level of technology that we really weren't even kind of thinking about considering a very short time before. So it happens quickly. Not everyone is a GPU expert. Not everyone dives in and learns to program them, but they end up affecting everyone's life in a variety of industries now, including aviation and medicine. Okay, enough slides. Let's take a look at some demos. For this, I'm actually going to use something it's the same engine, but it's a site that I'm kind of more fluid at using, because I've been chipping away at it for a long, long time. This is something that I wrote when I realized the book that I was working on in 1999 really wanted to be a pop-up book. And so, with that in mind, here we have a couple of toys built in. This is when I first started trying to figure out kind of what's a qubit. Here is a bit that goes from 0 to 1, right? And then when this is closed, we have all sorts of other operations we can perform. And then, but since this is running on a quantum computation simulator and not a physical QPU, we can also peek at this and see what's going on, right? As we rotate things and do Hadamard's and do, and then as soon as we open it, it will collapse to a 0 or a 1. And this is mostly just a little web toy to get a couple of basic concepts in, but then, let's take a look here. All right, so actually what I should do is on this. We looked at block spheres earlier, right? Let me make that a little bit bigger. So we looked at block spheres, and we can do kind of rotations around the block sphere of this particular state. This is a 1-qubit state that we're looking at. However, block spheres have a limitation in that, at least as far as I've been using them, that they don't scale up well to multiple qubits. And so I started using circle notation, and what we see here on the left is the 0 term, and on the right is the 1 term. If I open this watch, you can see it's very likely to be 0. All of these dark pixels are basically showing you the probability that it's going to be 0. And then the needle direction is showing you the phase. So if I open this, boom, it collapses to a 0. If I close it and then do a NOT, it's just swapping the terms, which is what an X gate does. If I do Hadamard's and rotations and phase, if I click the phase, which is a Z rotation, you can kind of see what's going on, which is the right-hand circle is just kind of flipping around. And I think that hands-on playing with stuff is really important, and this is why it's the focus of of the book. All right, so let's take a look at multiple qubits. Now we have 2 qubits. Make this a little bit bigger too. All right, so we have, we can start here. Here's our state vector, right? So this has 4 terms now, 0, 1, 2, and 3, because we have 2 bits in our number. Incidentally, while I've been working with, I'm currently surrounded by physicists in my work, and I was also at Bristol. Hexadecimal notation and kind of bit positions and binary numbers is something that I've actually given classes on for physicists, but it clearly comes naturally to anyone who's been a CS student for any length of time. All right, so in this case, what we're going to do is we can see we're going to write the value 0 to the 1 qubit and 1 to the 2 qubit. All right, so it just, boom, write that. And so what we've done is to write the value 2 to our register. And here you can see there's the code, right? So we write the value 2 to this quantum register. And if we were to read it right now, we can see that 100% probability we would read the number 2, which is great. It's not a great use of a quantum computer to do that. And so then if we do an X gate on the 1-bit qubit, you can see what that's doing. All it's doing is it's swapping things with their neighbors, right? If we do an X gate on a 2 qubit, it swaps things with their neighbors that are different, that differ in the 2-bit, right? And so, and if we want, we can even, I do a lot of this where we kind of take these guys and make them swap that way, right? So you can kind of get a sense for, kind of a slidey puzzle sense for what qubits do. And one mistake that a lot of CS students tend to make is that they get focused on the bits and on the qubits themselves, and really what they should be focused on is the state. And so now what we'll do is we'll do a Hadamard of the first qubit. There we go. All that did is, Hadamard is used frequently to make an even superposition if you start with a classical value. And then we're going to do a controlled knot. And this is the same as this operation we did a moment ago, except the control qubit means that it will only operate on terms where this bit is on. So to do that in your head, we'll take a look. For 0, no, that's the 1 bit is not on for 0. The 1 bit is definitely on for the number 1. So it's going to do something. So we'll see. There. And that's all that happened. We did the controlled knot. But now, as is mentioned here, these guys are entangled. If we were to read the 0, we would get a random value between this being 0 and this being 1. But the other qubit would also match it, because our only options are 0, 0, and 1, 1, which is 3. And then we can do another Hadamard if we want. We can do things like a controlled Z, which is like a controlled knot, except instead of swapping circles, all it does is to flip the phase of any circle where both of these bits are on. All right, so you see what's going to happen already. Boom. So looking a little bit further at something more complicated that we're also going to see later on when we talk about photonic quantum computers is graph states, or sometimes their cluster states are not always the right term for this. So we'll use the term graph states for now. But here what we've got is 4 qubits, so 0 through 15, right? Those are the values that we could produce by reading this. So 2 to the 4th is 16. We have 16 circles. And then also we have we can represent this we can represent the entanglements by a graph state. Now I'm going to stuff around a little bit. So if we Hadamard all of these guys, we will get an even superposition of all possible values for these. And then if we do a controlled Z, remember this is going to take any terms where this is 1 and this is 1 and flip them. So there they go. You saw them flip over here. And then also we've generated entanglement between these 2 qubits. So if we do this this, we can build a 4-qubit graph state. This program, this is a little sample program that builds every possible 4-qubit graph state, or at least every topology. And one of the things that's been really fun in working with this, I'll zoom these guys in so that you can see them a little better, is that each of these graph states actually has kind of a fingerprint in the state vector that is, at least for me, invisible until I'm looking at it here. So this guy, the star configuration will tend to have different orientations of it, but it'll have 2 here and 2 kind of spread out over there. And the one where everything's all connected has the little tail here and the arrow there. And so you start to notice and see different things. So for example, if I'm here at this particular graph state and I want to do some computation to change this to another graph state, then by looking at which circles would need to be swapped, I can tell what operations I need to do. So it's been very, very useful. There's also if we go over here, hypergraph, which in this case, this is a more complicated form of entanglement. And so we can represent that as an entanglement between these 3 qubits. And one of the things you can see is that fewer of the terms flipped. And in general, when you stare at something like this, if you have a graph state, you'll have all of these at the same probability. The smaller number of terms that are flipped, the more difficult the entanglement will be to generate on a quantum computer. So that's kind of fun. All right, moving right along. Let's see if we run this. This is just another graph state, right? This is 8 qubits instead of the 4 that we were looking at. The state vector, because it's 8 qubits, now we're starting to get into something that is big. So here we're looking at the entire state vector. And if we start with a Hadamard of everything, and then we flip the phase of one of the qubits, we get that, we kind of keep going, keep going, keep going. And this program, it turns out, is very long. This program is ridiculous. And so I'll skip to the end. And we've generated a cat in our state vector. And then what I use this for, when I'm talking to programmers and CS folks, is to talk about information density. You don't have 8 bits, you have 8 qubits. And in those 8 qubits, you've encoded a cartoon picture of a cat, right? And that's great. It's a bitmap, it's black and white. But then if I do play around with phases a little bit, I can get a little kind of a sunset gradation behind the cat. Now what's the information density? How much information is encoded in these 8 qubits? That's really interesting because it's not strictly binary. The rotations here and the amplitudes are continuous values, even though I can only ever read a binary value. That's weird. We also, by using similar things, we can express the no cloning theorem, which was mentioned earlier, which is you can give the students all of the tools and ask them to try and duplicate the value of a qubit you give them, and they'll find they're unable to do it. Then the other thing we can do is we can do a Grover iteration on these phases. And what Grover does is it turns a phase difference into an amplitude difference. And so now if we were to read this register, we would probably get a pixel that's not part of the cat. So, all right, moving right along. Let's see. Kind of an interesting thing here is quantum arithmetic. This is, I showed you earlier, a terrible implementation of addition. This one is, put that back down, bring this back up. This is 2 qubit-based numbers, A and B, and I've written the value 0 to A and the value 3 to B. And so in the circle notation, one of the things we can do is we can see that A, so first of all, So A is 0 and B is 3, right? And here, if we look at the entire state, we're plotting basically A against B. So A is 0 and B is 3. It's in the third row and the 0th column, right? And then just by doing the same swapping operations we were looking at before, we have a circuit here that implements A plus equals B times B. So this circuit squares B and adds it to A. And once it's done, notice this. B is still 3, but A is now 9, right? The square of 3. So hooray, that succeeded. Not a great use of a quantum computer because we just did basic math. However, if we come here and say, let's, instead of writing 3 to B, let's Hadamard B. So we do, they're both 0, see 0 and 0. We do the Hadamard operation. Now A is 0 and B is 0 and 1 and 2 and 3 in even superposition. And then we don't change the operations we do. The same circles get swapped exactly in the same way. But when we're done, B is still 0, 1, 2, and 3 in superposition. A is now a superposition of 0, 1, 4, and 9. And you can kind of see the parabola forming down here. Right, so it's a reasonable way to kind of show what quantum superposition is and what it does. And then, of course, if we read at the end, right, if we put a read at the end, then we can see we get all of these values, and reading it will only produce 1. Although the other thing we can do if we want is just read one of the qubits. See this guy. So now, once we've done our computation, we will read just that qubit and only some of the state will collapse. All right. Let's see. I think that the best, so one of the things that hasn't really been covered very much in today's talk so far is teleportation. And teleportation is something that gets freaky and spooky when people talk about it. And what I'll just show you very briefly here before wrapping up is the kind of circle notation, what the book does to demystify teleportation. So there's Alice over here, just visually, and Bob over here, and we're using an exchange to kind of simulate sending data to Bob. And so something that's very, very fun, I think, about the way that the book presents teleportation is that it begins with, let's physically actually teleport something. And thanks again to some of James Weaver's help, the book starts with using the IBM 5Q to, when you run the code sample, which is the only code sample presented not in the QC engine language, but in the native language, it's also translated to all the others. This uses an OpenChasm program which runs physically on the IBM machine. So as soon as the reader runs this code sample, they have actually physically teleported something that they made about 3 millimeters. There's also a super fun, there's also kind of a fun, whimsical experiment where we construct a fly using kind of the same thing I used to make the cat earlier, and then try and teleport it through a noisy channel and see what happens. All right, so in this case, the interesting thing here is what we can see is Alice makes a quantum state. It's just whatever she wanted to make. So we did our entanglement early on. Alice makes a state that is up and down, and I'm just using the colors here so that we don't have to squint at the little direction needles. So she's got a small probability up and a large probability down, and then she entangles it with this kind of entangled pair. And visually, let's take a look at what we've got. This is her original state, right? The little up and the big down. This is her state, but with a z flip on it. So if you flip this around, it would be correct. This is her state, but with an x flip. If you swap these circles, it would be correct. This is her state with both of them. All right, so another really interesting thing at this point is that if we take a look at these 3 qubits, right, we haven't read anything yet. These 3 qubits, suppose somebody broke into Alice's and Bob's offices right at that moment and then confiscated all their data and read it. Each of these would be a random 50-50 value, not depending on the others. Well, that's weird. And this is actually, it's not correct that it's not depending on the others, but each of these would be basically a random coin toss. So the information, although it is there still, you can see Alice's work, it's kind of cloaked in the fact that it's in the process of being teleported. And then when we do the read here, we do the first read, and half of our state goes away, and we get a 1. We do the second read. So the value we got was a 0 and a 1. And then given that information, that's enough to reconstruct Alice's state. Bob says, if this was a 1, swap them. And it was not. And then do a Hadamard. And then if this was a 1, do a Z, oh yeah, exchange them. That's right, I've got my Z flip here. And once you're done, you have Alice's original state that's been teleported to Bob. And I think with that, I will wind up and take any questions that there are. If there's a particular sample that you also want to see, that can be done. We have a little Shore thing here. But yeah, I'm happy to take questions now if we want.
Presentation, which is going to be here. But then I was thinking that if the next presenter who is in the room, can you hear me?
Yes.
Okay, so the idea was what we were talking about is Daniel's over there, and he's the next presenter. And if he connects and joins the Zoom, he could stay there in his seat and present. Except he's not going to do that because it's very slow. So he's going to go over there. If we do that, then I suppose we're going to disconnect the Zoom and then connect a little bit later. This was one of 2 presentations that EJ has. The other one is going to be mainly about the anatomy of a photonic cube quantum processing unit. So here's the book that you get. If you ask the question, first person who asks the question about this book and this presenter.
I have a question.
Dan Ellsworth, I'm currently at Colorado College, but my work is in HPC space, and of course GPUs have really taken off there in that space. And one of the things that's facilitated that is high-level language constructions, and so I'm wondering what your thoughts are. Right here we're down very much at the gate level, and we can think about with GPUs back when we used to read the screen buffer back. What are your thoughts about as we move to high-level language and how this is going to map across, or how we might be able to leverage what we're learning from the code samples and the work here as we think about how we teach this in higher level constructions?
I think that's a great question, and the part of what I was trying to wrap my head around as I had started to build all of this stuff was kind of, as we saw in the math example, being able to treat the normal right now is to treat qubits as individually addressable things, and in some cases that makes sense more than it does for a classical computer or a GPU, but then I think that it's very, very important for us to start, and also to encourage students to be leaning forward when it comes to taking lessons from software engineering into quantum computing. So for example, in this case, rather than dealing with the qubits of A and the qubits of B, there's A add squared B, and if we do 12 and 6 and 6, you're able to treat the the registers as actual registers instead of as kind of scientific objects, and that's, I think that becomes critical. One of the really fun things about quantum computing right now is that we're back in that kind of early to mid 70s era where a bit is a lot and a kilobyte is unthinkable right now when you're talking about quantum bits. And so in terms of simulation, in a browser here with this sim, you can do up to about 28 qubits, but that means the browser is allocating 4 gig of RAM, which is a lot for some laptops. And things slow down when you get that big. But it's I think that leaning forward on making complicated data structures and treating Q fixeds and Q floats and stuff like that, and using them in more complicated programs is going to be really interesting. It's going to be fascinating.
I have a question.
Yes, another question.
Yeah. So, so presumably you can add all. I mean, in your code, you can add all kind of entanglement measures. Okay. Essentially, to analyze the code itself. But the question I have for you is, what can we learn from the graphical standpoint about the complexity of the algorithm? So suppose I want to teach my students and I want to understand, or at least tell them, graphically, okay, this is a P algorithm, this is MP, this is MP hard. Is there something you can do that graphically shows you that thing?
So the thing that I've used for that, again, it's a really great question, because as things scale up, you end up running into this. The thing that I tend to use is this little toy model implementation of Shor. It's fully functional. It factors many numbers and not all. But what happens is you have a certain amount of complexity that's very easy to see. This first thing is a multiply by 2, and the multiplication is just doing bit shifting, right? Which computer science students get right away. And it's conditional on one of your precision qubits that you're going to do a QFT on later. And then what happens though is this starts very simple and friendly, but then when you get to, say, a larger implementation, you can start to see it going, oh wait, what am I? There. As soon as you get to a larger implementation and a more general implementation, and you end up having to do the modulo as a separate process, you can very quickly kind of watch your algorithm grow terribly in time, and then present the question, how would you use, which this is one of the primary questions in modern quantum algorithm design, how would you use more qubits to shorten the time? And can you do that? Can you make that trade-off for any particular algorithm between the gate depth and the number of resources required? It gets a lot more complicated for fault-tolerant quantum computing, obviously, but
Right,
even
yeah. I understand that, but is there any way that you can use, some measures plus graphics, as you showed before about this, this circle notation, that can guide you?
I have not considered that, but it's well worth thinking about.
Because there could be some use of this, graphical way of understanding.
Yeah, definitely. One of the things that ends up becoming very visible is if you're doing iterations of a Grover search, you can see things go up and down in probability, and you can see, how many times you might have to run a particular algorithm before you'd be likely to get an answer that's valid. But yeah, no, I don't know of any way to graphically kind of intuitively do the run complexity. That's interesting.
there was another question too. Just a second, yeah.
Yeah.
We always have time for questions, please.
Thank you, EJ. That was really great. I love the circle notation, and and it seems like you first invented it as a pencil and paper thing, and then you brought it to life in your simulation. Is that right? And can you describe more? And and are people starting to adopt it? Because it seems like Gerardo was pointing at. It seems like it really, at least for me, it built a lot of intuition, and I really appreciate it. Thank you.
Yeah, you're very welcome. When I first showed up at University of Bristol, I wasn't sure yet that circle notation mapped to anything useful. And then as I started working with a physicist and realizing it did, I would do my own sketches and whatnot. And the first time I ever saw a whiteboard with circles on it that I hadn't drawn, I got a little weepy. I did a white paper a little while ago that you can find just searching probably QC Engine circle paper. But in this, I sort of walked through. I actually physically made graph paper so that I could play around with this stuff. And then this white paper shows a lot of the swapping stuff that we were looking at that I had not really considered visually animating and all of this. But then when you get to the end of it, it actually goes through a whole teleportation by hand on paper. And so the first real adoption of it was it got used to teach summer school to high school seniors at University of Bristol. And then the second real adoption was when O'Reilly said yes to let's do a book. So that, no idea, but I do know that in one of the other quantum sims, there are lots and lots of quantum sims online, and I think Quark is another one where recently I looked and I saw circles displayed for the complex numbers, and that it I think helps there too. In fact, if I remember correctly, they do separable states way better than I do.
Okay, we're going to take a break, but before that, let me just say something to you. So there is something a little bit unfortunate about this conference. I mean, the whole situation, ambiguity, uncertainty, and the fact that some people couldn't come and so on. But every cloud is a silver lining. And EJ mentioned two things. First of all, that we're going to have Q Sharp a little bit later today. And that's the sad news because Sarah is sick. She is in Washington, in Seattle. And she says she has no voice, which means that we lost a presenter. And we were talking to Professor von Baer, maybe his presentation is going to be longer or maybe start, whatever. The thing is that he also mentioned Maria Mihailova from Microsoft. And then I said, why didn't I think of that? How else can you replace a presenter that quickly? So I emailed her. I said, 3 p.m., can you step in for Sarah and then do Q Sharp? 30 minutes is fine. Tell us what you teach at the University of Washington. And she said yes. So
wow.
Because of this, yeah, just astonishing. So we're going to take a 5-minute break. We're going to switch. We're not going to switch anything. Daniel Koch, who is here, live presenter, the first of the two that are here, is going to present Qiskit. So 5-minute break, and we'll convene. The same setup stays. All the Zoom is going on, but just 5-10 minutes break, bathroom and refreshments. Thank you. Thank you, EJ.
Thank you. That's a treat because Maria wrote all of the Q Sharp implementations of the book samples.
Yeah.
All right.
All right.
Thank